In question number 19, it asks us to find the length of the hypotenuse of this pattern for each successive triangle. And as I calculate this, I'm using Pythagoras, so 1 squared plus 1 squared equals 2 squared, so we end up with square root 2. Root 2 squared plus 1 squared is going to be 3, so we end up with root 3. And the pattern is going to continue, and we're going to end up with root 4, root 5, because we're just basically going to square that edge here, this one here, and we're going to add 1 squared to it, which is just going to increase that by 1, and then we're going to square root it. So the pattern continues that way. So it says, use the pattern to predict the length of the hypotenuse of the 50th triangle. So the pattern that we see is that the term inside the root increases by 1 for every hypotenuse. And to predict the 50th triangle for part 2, predicting the 50th triangle, we know that the first triangle is root 2, the second is root 3, the third is root 4. So the 50th triangle is going to have a hypotenuse of square root 51. It's going to be one more than the triangle number. So part 3, it says, how many of the first 100 triangles have a hypotenuse length that can be written as a mixed radical? Okay, so this is quite more of an involved problem. First of all, we need to know that we have roots from root 2 all the way to root 101. And the ones that can be written as a mixed radical are going to have the mixed part gives us a whole number, so it has to have a perfect square factor, but it also has to have a radical part, so it has to have a part left over that is not a perfect square. So we can start with, I'm going to start with the largest numbers, and we can start with, root 64 and ask, well, what does root 64 divide into any numbers bigger than, or any numbers from 2 to 101? Well, it will divide into 64, but that's a perfect square, and there's no other numbers smaller than 101 that it will divide into. So there are going to be none based on that root 64. And then I could have started at 81 or 100, but we know that those ones won't work. So starting at root 64, we probably can tell that that one wasn't going to work either. So I go down to the next perfect square. So I go to root 49. And I got to ask myself, what numbers between 2 and 101 are divisible by 49 and have a factor left over? So that's going to be root 98. Okay, because that's divisible by 49, but it's going to have a factor of 2 left over, so I'm going to end up with root 49 times root 2, and this becomes 7 root 2. So I can generate a mixed radical based on there being a perfect square factor and something left over. And with 49, that's the only one that we can use. So then I go to the next number, which is going to be root 36. Okay, so then I need to ask myself, what numbers between 101 and 2 are divisible by 36, and the only number other than 36 itself, which is a perfect square, is going to be root 72. And so root 72 is going to be 36 times 2. So this is going to generate a mixed radical of 6 root 2. And then are there any other numbers? The next multiple is going to be 108, so that's not going to work. So I'm going to go down to the next one, which is 25. Now 25, there are a number of numbers that can be divisible by 25. So one is 25, but 25 is a perfect square. 50, and 50 is not a perfect square, so that's one we can use. 75 is not a perfect square. And then we get to 100, which is a perfect square, and again, there's no leftover parts for the perfect squares, so we can't use those. So 50 then becomes, we take out the perfect square of 5, and we're left with a factor of 2. With 75, same thing, we take out the perfect square of 25, but we're left with a factor of 3, and that gives us the mixed radical parts. We can move to root 16. 16, we can do root 32, root 48, root 64. Well, 64 is a perfect square, so we're going to skip that one. We go to root 80, and then root 96, and that's all we can do. So these have perfect squares of 4 squares, so the 4 comes out. We're left with 2 here. Here the 16 comes out, and we're left with 3. Here that 16 comes out. We're left with 4. Wait a minute here. We're left with 5. Yeah. 4 root 5. And then for this one here, we're going to be left with 16 times 6, so 4 root 6. And then we move on to root 9. Root 9 is going to be 18, 27, 36 is a perfect square, so I'm going to skip that to 45, 54, 63, 72, which we've already done, so I'm going to skip 72. And then 81 is a perfect square, 90, and 99, and we're at our limit. So then converting these into perfect square or mixed radicals, the perfect square part of 9 becomes 3 on the outside, so 3 root 2, 3, and we're left with 3 in here. This is 9 times 5, so it becomes 3 root 5. 9 times 6, so it becomes 3 root 6. 9 times 7, so 3 root 7. 9 times 10, so 3 root 10. And 9 times 11, so 3 root 11. And then lastly, we're down to root 4. And so we're going to go root 8, root 12, root 16, we'll skip root 20, root 24, root 28, root 32, root 36 is a perfect square, so we'll skip that one. Root 40, did we have root 40 in here? No, so root 40, root 44, root 48. Okay, root 48 we already had, so we're going to skip that one, so we're going to go root 52, root 56, root 60, there's quite a few of them in here. Root 64 is a perfect square, root 68, root 72 was, I think we had that one up at the top there, root 76, root 80 I think we had before, root 84, root 88, root 92, 96 we already had, 100 is a perfect square, so those are all the ones that can be expressed with 2 in a root. So 4 times 2, so we end up with, the 4 comes outside, we're left with 2. This is 4 times 3, so we end up with 2 root 3. 4 times 5, so 2 root 5. 2 root 6. 2 root 7. 2 root, I think we actually had 32 in there because that's 4 root 2, so we don't need to keep that one again. So this becomes 2 root 10. 2 root 11, 2 root 13, 2 root 14, I think that is, 2 root 15, 2 root 17, 2 root, what's that one going to be, 19, 2 root 21, That's going to be 2 root 22. And lastly, we're going to get 2 root 23. Okay, so those represent all the mixed number possibilities that we're going to get when we look at the hypotenuses of the first 100 triangles. So there's quite a few there.